Welcome back, everyone. We are to the final section in Chapter 2. We're going to do a different type of differentiation or derivatives. And it's called implicit differentiations, and we'll run into something called related rates. In our work until now, the functions we need to differentiate were explicit, meaning y is a function of x. The problem is there are times when it may be difficult or nearly or actually impossible to get y by itself as a function of x. So an example of that they have right here, and you can see that there's no way to get y by itself because we have y, a polynomial, and then we have e to the y, which is an exponential function. So there's no way to get y by itself in terms of a function of x. We can still find dy dx. I want to point something out that if I have y equals x to the third, and I find y prime, I'm actually taking 3x to the second power times dx over dx. Now, we don't write that ever because dx over dx is just 1. So this hasn't really been an issue that we've needed to deal with, so we just ignored it. However, when we have x's and y's kind of buried in there together, like we do for example 1 here, we have a problem. So if I apply d over dx to this whole piece here, well, that's going to give me 4x to the third dx over dx plus 4y to the third dy dx equals 0. And it's 0 because 82 is a constant. Derivative of a constant is 0. Now, I want to point out I didn't need to write this because that's just 1. However, dy dx, that's my goal. That's what I'm shooting for. That's what I'm trying to get by itself. I'm going to note that I can divide a 4 out all the way across. And if I subtract that x to the third, I'm going to get y to the third dy over dx equals negative x to the third. So dy over dx is going to equal negative x to the third over y to the third. And that actually is going to be our answer here as far as our implicit differentiation goes. I know it's a little bit weird. It's a little bit different way of looking at things. Next up, it says we want to use this. Remember, this is our slope function to find the coefficient of the tangent line through the point 3, 1. So m at 3 is going to be 3, 1. I should be clear. Is going to be negative 3 to the third over 1 to the third, which is negative 27. So there's my slope. And I'm going to use y equals mx plus b. So y is 1, m is negative 27, x is 3. This means 1 equals negative 81 plus b, so b equals 82. So our equation is going to be negative 27x plus 82. And there is our tangent curve, tangent line, I should say, to the curve. X to the fourth plus y to the fourth equals 82. Right, for example 2, I don't have enough space here to do this, so I'm going to go to a separate sheet of paper. And here I have the function. We are looking for dy dx. I got to be careful here. I have product rule. So I'm going to have to go derivative the first times the second time plus x to the 39th times the derivative of the second. And here we go. So this gives me negative 26 times 9. So negative 234 x to the 8th plus 5 times 39 x to the 38th y plus 5x to the 39th, and derivative of y with respect to x is dy over dx, which again is what I'm looking for. This is going to be 8y to the 7th dy over dx equals 0 once again. You can see why I needed more space. This one's a little bit more messy. All right, my goal is to get the dy dx by itself. So what I'm going to do is I'm going to move and what is 5 times 39? 5 times 39, 195. So minus 195. Yeah, 195. X to the 38th y. And that's going to get me 5x to the 39th dy over dx plus 8y to the 7th dy over dx equals 234x to the 8th minus 195x to the 38th y. All right, so I now have the dy's by themselves on one side of the equation. I have the non-dy terms to the other side of the equation. I'm going to factor out a dy dx. And again, I'm still trying to get dy dx by itself on one side. So I'm going to go ahead and divide both sides. Which means dy dx is here. And so this is our first answer that we are looking for. And that's the first part. The second part is they want us to find the tangent line at the point 1, 1. All right, so I need to find m, which is my dy dx, specifically at x equals 1, and y equals 1. This is going to be 234, 1 to the 8th, minus 195, 1 to the 39th, times 1, over 5 times 1 to the 39th, plus 8 times 1 to the 7th. It's very nice they had everything ones for us. So this is 234 minus 195 over 5 plus 8. Let's see what we get. 234 minus 195. And that becomes 13 divided by 13. So of course, very nicely, we get a slope of 3. Yay. I now need to figure out, so I have a point at 1, 1, and I have the slope of 3, so y equals mx plus b. This is going to give me 1 equals 3 times 1 plus b. b equals negative 2, it looks like. There we are. So again, it's a little messy, a bit of work there. I'm going to go back to our other problem. So that all goes there. So now we are to the area of a circle. And if you remember the area of a circle, now in this case, we are assuming that a is a function of t and r is also a function of t, and we're going to be taking the derivative with respect to t. So we're not taking the derivative of a with respect to r. It's going to be a with respect to t and r with respect to t. So dA over dt is going to equal 2 pi r dr over dt. And it says, let this be the area, and we want to find dA dt when r equals 1 and dr dt equals 5. So they've given us all the information. R is 1, dr dt is 5, and that gives us 10 pi. And so that is the rate at which the area of this circle is changing. It doesn't give us any units, but it would be something like square centimeters per second or per minute or whatever it is that we're trying to get to. All right. And our last example for chapter 2. I'm sorry, we have 2 more examples. One of them is we have a spherical snowball is melting in such a way, by the way, the volume of the sphere is 4/3 pi r cubed. Spherical snowball is melting in such a way that its radius is decreasing, so dr dt is negative 0.2 because it's decreasing. At what rate is the volume of the snowball decreasing when the radius is 14 centimeters? So they give us that r is 14, and they want to know dv over dt. That's what they don't know. So we're going to find dv over dt is going to be 4 pi r squared dr dt. R in our case is the 14. dr dt is negative 0.2. And that's going to give us, let's see what we get, negative 8 times 14. 14. So I'm getting, oops, I didn't square the 14. Let's do that again. Yeah, so let's do 4 times 14 squared times negative 8, negative 0.2, 0.2. So I'm getting negative 156.8 pi is what I'm getting. And this is going to be in cubic centimeters per minute. And so let's multiply that times pi. So I'm getting that this is about negative 492.617 cubic centimeters per minute. Not too bad, not too difficult. And we're to our last problem. A company's revenue from selling X units of an item is given as R equals 1200X minus X squared. If sales are increasing at a rate of 500 units per day, how rapidly is revenue decreasing in dollars per day when 310 units have been sold? Okay, so again, we want to view R as a function of t, time, and X is also a function of time. So it's no longer R as a function of X, which is what we've been dealing with. So this is going to be a little bit different. So I'm going to take the derivative, and that's going to give me 1200 dx dt minus 2x dx dt. And they have given us sales are increasing, so they're giving us dx dt is a positive 50 units per day, 50. And we're looking for dr dt. So we have all of our information. They also give us that when x is 310. units. So we're going to plug in what we have. We have 1200. dxdt is 50 minus 2 times 310 times 50. And let's see what we get. So I'm getting about $29,000 per day. Not too shabby. And that is going to do it for chapter 2 for us. Thanks, everybody.